Okay, the second of our 11. Wow, sounds pretty terrifying, doesn't it? Of our 11 segments regarding graphing. Let's just take a look at what we've done. We've done a wee bit of work with sine and cosine, and we'll do more on that today. We'll get into the rest of this another time. I want to pick up where I left you off, even though you've been back to class and you probably finished this up. Let's just show where the sine function did plot. Okay, the sine function would have plotted right there. And then you did the cosine function, and it plotted right here. Okay? So we have the sine going like this, and down and up again to 0. So starting 0 at 0, zeros again at 180, goes down to its low of -1 at 270 degrees, and then back up to 0, ready to start the whole cycle over again. Cosine begins at 1. When the angle is 0, cosine is equal to 1. It goes down to 0 when it gets to 90. It keeps going down to get to its low point at 180 degrees, that is -1, and then it comes back up to 0 at 270, and when it returns to 360, it's 1 again. I want to talk about the nature of those two graphs, sine and cosine. They are periodic. I thought I would use electricity. As some of you know, that's my background. I worked in electrical or electronics for most of my career. Periodic functions. We talk about electricity. In electricity, you either have direct current, which has a polarity. You can even make yourself a little battery using some metal and a lemon, right? It has a polarity or direction that doesn't change over a long period of time. When we put our batteries in, we're very careful about that. Otherwise, the device won't work. Put your positive to the positive terminal and your negative to the negative terminal. Although the intensity of the current may vary from moment to moment, the electrons are always flowing in the same direction through the circuit. This is not periodic. However, the current that we use more of the time is alternating current. We plug into the wall, we get alternating current. The polarity keeps reversing. So you may have positive polarity and then negative polarity, positive, negative, positive, negative. It just keeps going back and forth. That's why they call it alternating current. The electrons move back and forth. The current ebbs and flows. But our devices see, they're not bothered by that fluctuation. They see what is a fairly constant for them voltage. There are other places we can see this concept of a period. The length of time between one repetition of a pattern or one wave cycle and the next. If you take your pulse, you'll get a thump, thump, thump. If we put you on an EKG machine, we would see that represented there as well. There is a period between each of the pulses. And for a sine wave, which we plotted this one right here. For a sine wave, there is a period which is the length between one full cycle and the start of the next full cycle. This period from when this is ascending into zero to when it is ascending into zero again is 360 degrees, or perhaps if we express it in radians. Now the clue that we're going to express in radians is right here. We're expressing the angles in radians here, so we should give our answer in radians. We know that is equivalent to 360 degrees. For cosine, which plotted from a peak of 1 down to a valley of -1 and back up to that peak before it repeats again, we have the same period, 2 pi. Now this is going to be important for you to know, so it's good that you did that plot. It kind of, I think, cements it in your mind, in your memory. I'm going to be using your calculator for a few minutes here just to understand how we can get the correct window, a graphing window. Let me move something here first. These are my windows. I made them in advance. The window that you're being advised to use here on your graphing calculator, oh, let me get it on there right. Let's move it over, Jim. I wish it would stop trying to convert my hen scratches into something in English. And on this one, now we're going to talk about these in just a moment. First, I'm going to say what you would see on your calculator. First, I'm going to show you what you would see on your calculator. X-min, the smallest angle that you expect to view. So if the smallest angle I expected to view was -360, or 2 pi, I would set X-min to -2 pi. Now, this better be in radians, right? I'm going to do my graph. Yes, it is. It's in radians. So we'll go to Window, which has its own button, and I'm going to put in negative. It's important to use this negative that's in parentheses. This negative over here is an operation. It's going to try and subtract something. You don't want that. You just want to note that your value is -2, second function to get pi. Now when I hit enter or go down, it's going to convert it into decimal, but it's as accurate as your calculator can get it. X max is the greatest angle to view, and we know that what I've defined as my window here, I only want to go up to 2 pi, so I'm going to put in 2 pi for that. X scale, that's the space between the x-axis tick marks on your graphing window. I think pi divided by 4, yeah, that would be consistent with what I've got here. So let's do that. Pi divided by 12 is also very good. That gives you 15-degree increments. Okay, so pi divided by 4. Now, y minimum, that's going to be the smallest ratio possible. or the smallest ratio I expect to see. That's my value, and that's going to be negative 1. Y max, the largest ratio I am expecting to see, that's going to be my peak of 1. X scale, that's going to be the space between the y-axis tick marks, and if I want to match to this graph, it would be, it wouldn't be 1/4, it would be 1/2, but let's make it 1/4. 1 divided by 4, that'll give me one more set of tick marks there. And the resolution, let's leave it at 1. So I have a window now, which when I put in y equals sine x, let's do that, y equals sine, and you know where to find the x? Right here. Now, what it chooses when you hit this button depends on the mode that you're in. Let me show you that. Down here, this is function, parameter, polar. Okay, so we're going to be in function. And now let's graph it, which is exactly what we expect to see, right? Here's in the negative part of the x-axis, we are seeing, this is in quadrants 2 and 3, we're seeing this one. And then it repeats. So we're seeing 2 full cycles using this same window. Except let's put in y equals cosine. Whoop. Back it up. Clear. Cosine x. And then we'll graph it. We didn't change the window. The window will stay the same. And now we see it starting at negative 2 pi, going down, 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 and coming back up when it gets to the origin angle measure of 0, and repeating again. Suppose I wanted to see this in degrees. Change my mode to degree. And then I'd have to go back and change my window. My window would be negative 360 to 360. That's my angle measure on the x-axis. And this would be 45. Nothing would change about my y. Now let's graph that for cosine. Looks just the same, doesn't it? Because my mode and my window are in alignment. Most of what we're going to do will be done by hand. Compare the sine and the cosine graphs. What was the same and what is different? Okay, here's my sine graph. Here's my cosine graph. How about the shape? Is the shape pretty much the same? Oh, whoops, I'm sorry about that. Don't mean to do that. I can actually pick this up, I think. And I can move it over here. Oh, no, I don't want to move that. I want to move this one. And we can see that the shape is pretty much the same. Okay, so the shape is, how would we describe that? Sinusoid. Okay. What's the same? There's sinusoid. There's no difference in the shape. The period. The period is 2 pi. And they're both 2 pi, so there's no difference in their period. What about their position? Well, there is a difference, isn't there? The cosine shape is shifted. It has a shift of 90 degrees, or it's got a pi over 2 horizontal shift. We're going to talk a lot more about shift as time goes on. So really the only difference between these two is where they are located on that coordinate plane. Notation for intervals. You may have had this before, maybe you haven't. But I want you to be clear about it, because when you get this on a test or a quiz, or later on next year in your studies, you want to be able to interpret this correctly. If we are including the boundary point, we use a bracket. So you notice this one, which includes 180 degrees and 360 degrees, we use a bracket. We can refer to that as a closed interval. When you include the boundary point, it's called a closed interval. If you're excluding the boundary points, you use parentheses. That would be up to, but not including whatever the boundary point is. So here I have a closed interval. Here I have an open interval, not including the boundary point, and we can have mixed. We can have half open by having this one include the 180 and this side of the boundary, this side of the interval, not include 360. That's a notation. Critical points for graphing sinusoids. You are going to be asked to graph without using your calculator. You'll want to use those values that are, what did we call them, sort of the magic 3 and your quadrantals. So we could do that with the primary period of sine, going from, notice this, we're going to include the 0 up to 360. Well, I'm not going to include the 360, however, I am going to graph it. So the period, the reason we are not going to include 2 pi or 360 is because when the next one begins, the next cycle begins, it begins right there. So we don't want to count it twice. But as long as you graph the beginning, the end, the middle, the beginning, the end, the middle. Here we are, start, the end, and midway. And then you get 1/4 of the way, that's halfway to the middle, and 3/4 of the way, which is halfway to the end, right, from the mid. If you graph those points, that's really all you need, as long as you recognize what the sinusoidal shape looks like. It's going to look like this, starting from 0 for y equals sine x, and it's going to look like this for cosine, starting at 0, where the ratio is 1. I wonder if I can just pop those in. I can. So we've got, with just those 5 points, you could, and for me, when I'm grading you, if you have those 5 points located correctly, accurately, and your curve is a little shaky like mine is, that's still 100%. I don't expect you to be an artist here. I do expect you to be able to accurately plot these 5 critical points. Sketching a parent sinusoid graph by hand. Locate the key points. Well, for the parent sine, our x-intercept is our beginning, and the next x-intercept is our ending. And our middle is also an x-intercept. So, all right, and our maximum comes midway between these two intercepts, and our minimum comes midway between these two. What a nice relationship that is. I'll show you why it works so well for us. So, our first critical point is located at, my y, of course, is 0 for all my x-intercepts, and this is at angle 0. This next one is at angle pi, and this last one is at 2 pi. So halfway between these is where I see my maximum of 1, which is at pi over 2. And midway between pi and 2 pi, I find 3 pi over 2. Now we know what my y value is for the minimum. It's -1. For my maximum, it's 1. And for all x-intercepts, it's 0. So these were my y values. And of course, these are my x values. Let's do this as well for cosine. You need to know these. These are really important to know. Of course, cosine starts at its maximum of 1. Then it has an intercept at 1/4 of the way. When you get midway, it's at its minimum of -1. 3/4 of the way, it's back to x-intercept, and then to its maximum again. So these are my y values, the value of the ratio. My x values are 1. Excuse me, I didn't mean that, do I? No way. My x value is not at angle 1, it's at 0. My x-intercept, the first one, is at pi over 2. I get to my minimum value at pi. I come back to my x-intercept at 3 pi over 2. And I end that first cycle at 2 pi. Now these key points, as far as the x go, they match. But because this one is shifted a bit, it's a different sequence for your y values. This is important to you in being able to do a hand sketch. I expect you to be able to sketch these graphs by hand. Now, if we looked at a table of values for sine, we'd have these values. You should begin to know what the, of course this doesn't have all of them, does it? Oh, yes it does. It has enough. It has the 5 of them. In fact, it has even more than that. We've got 0, 1, 0, -1, 0. So the 5, let me just mark the 5 critical ones right here, right here. We've got more than that because in this table of values I put in all the 45-degree reference angles. So that would be this one, this one, this one, this one, this one, and that would be one full cycle of sine. Let's do the same thing for cosine. We have our 5 key values. I'm going to use these for graphing. And if you plot these accurately, you should have no trouble doing that, then you'll get 100%. There you go. And back again. Let's just take a moment to remind ourselves about domain. For both of these, all real numbers are possible angle measures. The range is limited. The range is between the peak and the valley. For the parent function on both of these, it is between 1 and -1. You're going to model with these, and when you model with these, you're going to be interested in the shape, if your model can be a sinusoid, the period, so for this we've got a period right here, and you're going to be interested in the amplitude. Whoop. The amplitude is the distance from its axis trying to move this without changing its shape. Okay. The distance from the axis that runs down the middle of it to its peak. Let's look at the definitions. The cycle, that's the portion of the graph from one point to the point at which it begins to repeat itself. So here we have it for, here's one full cycle for the sine graph, and I actually can get one full cycle. I'm placing it a little bit different place. I'm not starting at 0, I'm starting at -π/2 for cosine, but still that's one full cycle, isn't it? It meets the definition. The period of a periodic function is the change in x that corresponds to one cycle. So for both of these we know it's a change of 2π. And if you look at this one, if you're going from -π/2 to a positive 3π/2, that is a change of 2π. The amplitude of a sinusoid, in the case of the sine graph, it's 1. And guess what? In the case of cosine, it is also 1. Stretching or shrinking vertically. We are familiar with this from back in algebra and all we knew about quadratic functions and their graphs. Here is a parabola, the graph of the parent quadratic, the very simplest quadratic function you can have, y equals x squared. What value of a would vertically shrink the parent quadratic to the shape of this red one? Well, let me put that red one right up here. We'll match the vertices. So put the vertex right at the origin. When the parent has an output of 4, these are 2 by 2 grids, 2, 4. This one that I just put up, the red one, has an output of only 2. A is the vertical multiplier, so it looks like this A is less than 1. Let's take a look. Indeed, it's 1/2. There we go. So the value of A, which would vertically shrink this, so it goes up only half as fast, is 1/2. We can do the same thing in trigonometry. A is a vertical multiplier. A vertical multiplier in a trig function is called the amplitude. Okay, so what amplitude does y equals sine x have? We know that. It has an amplitude of 1. And where is that 1? Well, we don't usually write it in, but it's right there, isn't it? What amplitude does the green sine wave have? Well, let's do what we did with the quadratic and move this into the same position. What I'm doing is I'm matching the origin. We know the definition of amplitude. It's from the axis which runs in the middle of the sinusoid to the peak. Let me mark that. So from this point here up to the peak, that's what we're talking about. That's the distance we're interested in. What amplitude does this green one have? I hear some of you telling me, certainly you're right. Two. There it is, 2. So what did it do? Did it shrink it or stretch it? Yeah, it stretched it. Find the amplitude of each function and use the language of transformations to describe how these graphs are related. Okay, let's see. This first one, we've got the parent function, what I call the parent function. Its amplitude is 1. The second one, this is cosine. We've got an amplitude of 1/2. This is a vertical shrink of the parent graph by a factor of 1/2. And for number 3, ooh, that's an interesting one. We've got an amplitude of 3. Ignore the negative for a moment. We've got an amplitude of 3, which is a vertical stretch of the parent graph by a factor of 3. What this negative is going to do, it's not going to actually affect the amplitude. What it's going to do is reflect the graph on the x-axis. We'll talk more about that later. Okay, but this is the thing to pay attention to here. Okay, this is right in your book. On your calculators, you want to graph the following curves in, please, radian mode. Now you're going to set your window so that x min is the smallest angle you want to view, which if we're looking at this, it's kind of hard to tell. It's set to radian, so put your mode to radian. And then put your x min, I would say that is about a -0.5, I'm not sure, -0.5 radians. The greatest angle you want to view, let's see, this goes up to 5 radians, this must be 6, let's say positive 6.5 radians. I think that'll be about right. The space between the tick marks is 0.5 radians. The smallest ratio possible, what do we see as our least number, is -4. Our largest is a +4, and the spacing between these tick marks is 1. And our resolution, we don't have to worry about, that's going to stay 1. The coefficient, or the multiplier of the function, see it right here? And what is this one? This was actually a 1. Is its scaling factor. In sinusoids, this is the amplitude of the curve, the distance from the central axis of the curve to its maximum. Oh, I already had these all worked out. I didn't have to even write them down because, well, no, I'm not going to use those. We'll use what matches what he has in his diagram. I think that'll work better for you. The amplitude of, now this is a general formula here. We put in A to represent the amplitude, is the largest value of y, and it's given by whatever is the absolute value of A. So in the case of this graph, the amplitude would be 1, this one would be 2, 4, this one would be, remember, absolute value, 0.5, absolute value, 3. We define the range of the curve as being from negative A to positive A. We define the orientation of the curve this way. If A is positive, it's going to match the parent. That is to say that sine will rise, that ratio will get larger as we move away from 0. If A is less than 0, it's going to be reflection. It'll go in the opposite direction. So as we move away from angle 0 towards 90 degrees, it gets smaller instead of larger. Just the opposite. We define vertical change of shape. It either stretches vertically, as this one will and this one will, and this one will, so we have 3 of them that will stretch, or it shrinks vertically. We only have one that's going to do that, or it stays exactly the same height as the parent, which is going to happen with this one. Well, that is the parent graph. This is the piece that you need to be starting on. Let's see. What I'd like you to do here, we can start one, is fill out all of this. So the amplitude on this one would be 3. The range would be from negative 3 to positive 3. The critical point angles would be, now remember what we're thinking of here, the start of the cycle to the end. Let's do where it starts. It starts at 0, and we're going to do these in degrees, and it ends at 360, because we know the full cycle is 2 pi, or 360 degrees. The midpoint is going to be at 180 degrees, and halfway between these, 90, oh come on, and 270. Critical point angles. And its orientation, because this is positive, we say its orientation is normal. For the next one down, which is negative, that one's going to be reflected. Is this being stretched or shrunk? Because this is greater than 1, the absolute value of this is greater than 1, this is a stretch. Okay, so we'll finish the rest of these in class. It'll be simple enough. Complete in class.